Well, here's the table. We'll start by using the table, and then we'll see if we need to have a deeper understanding.
I learned another trick for this besides this table.
Yeah.
It's okay, this phrase even thermal con.
Uh-huh.
And if the number of electrons is even and there's heat, then it's conrotatory.
Mm-hmm.
If the number of electrons are odd and it's heat, then it's disrotatory.
Right.
Or vice versa.
And then,
but if it's
right.
odd and light, then it's still conrotatory.
Okay, yeah, I think that'll work. Let's get back to that in a second. First of all, what do we mean when we say the number of electrons here is 4n? First of all, what we mean is the number of electrons that are participating in the reaction. Well, what would be the smallest possible number in this series? In this series?
0.
Yeah, but you can't really have a reaction with 0 electrons.
2.
I don't think this ever could be 2. Well, n has to be an integer. I should emphasize that n has to be an integer here. So if n was 1, you would have 4 electrons. Or if n was 2, you would have 8 electrons. You might have been confusing this with Huckel's rule if you started looking at that. I don't know. But anyway, this is different from Huckel's rule. If n is 3, this would be 12. Anyway, the point is, these are all just multiples of 4. That's really a simpler way to put it. This is the category where the number of electrons is a multiple of 4. So what's the first entry in this series?
2.
2. And then the next one is?
4.
Actually, not really. 6. Because if n is 0, this gives you 2. But if n is 1, this gives you 6. And then?
6, 10.
Right. 10. Now, really, maybe this algebraic way of putting it is just confusing. Maybe an easier way to put it is just start with the number 2 and then keep adding 4s. This series is when you start with the number 2 and keep adding 4s. And this series is when you start with the number 4 and keep adding 4s. Maybe that's an easier way to think about it. Maybe we don't even need this algebraic way of putting it. This is kind of a pompous mathematician's way of putting it. But we can just say this is the series where you start with 4 and you keep adding 4s. And this is the series where you start with 2 and you keep adding 4s. Now, you were mentioning that the trick that you learned was even thermal con.
Mm-hmm.
Now, I think that'll work, except this does not mean that the number of electrons is even, because the number of electrons is always even. I think what you meant is that this is when the number of pairs of electrons is even, or maybe the number of electron pushing arrows is even.
I think, I'll tell you in a second.
I think it's number of double bonds.
Yeah, I think it's number of pi bonds involved.
Right, although sometimes it's a sigma bond that's involved. So maybe the best way to put it is the number of electron pushing arrows that are involved.
Yeah, that's it. Because when you break a sigma bond, it still turns it into a pi bond.
That's
so
true.
The pi bond is kind of involved.
That's true. Okay, well, for after all, notice that if there are 4 electrons total, that would involve 2 arrows, right? The number of arrows is always half the number of electrons, because each arrow represents 2 electrons. So here's where we would have 2 arrows, or 4 arrows, or 6 arrows, or 8 arrows. But here's where we would have 1 arrow, or 3 arrows, or 5 arrows, or 7 arrows. So in this case, the number of arrows there would be an odd number of electron pushing arrows, and here there would be an even number of electron pushing arrows, since the number of arrows is always half the number of electrons. And then I think this will work. So if you have an even number of arrows, it should be thermal. Thermal should go with conrotatory. Well, here we have the even number of arrows, and thermal does go with conrotatory. And then once you know that, you can kind of figure out everything else on the table, just kind of on the the opposites rule. So the photochemical should be the opposite, that's disrotatory, and then the odd number of arrows should be the opposite pattern. So whereas thermal here is conrotatory, thermal here should be disrotatory. So if you just remember that everything is kind of an opposites pattern, all you really need to know is, all you need to memorize is one entry here.
Yeah, and it's for that phrase, if you change even, then you change it to disrotatory,
right.
And then if you change thermal, then you change it back to conrotatory. So
yes.
For every one of those that you change, you just change the end.
That's a really good way to think about it. That's right. That is a good way to think about it. That would work. Okay. Is that something your instructor told you to use? Or?
No.
But that sounds good.
Yeah.
That sounds good. Now we have to see how to use this to solve problems. Now we need to draw the product. So first I'm going to show the mechanism. This is going to be a ring opening, so I have to start by breaking this sigma bond. Now let's work through this together. Okay, yeah, let's work through this together. Maybe I shouldn't have drawn it like this. But anyway, so is this going to be conrotatory or disrotatory? We have an even number of arrows. 2 arrows, even number of arrows. So, and it's thermal, so it's going to be conrotatory. So have you guys learned the finger trick? Or have you seen the finger trick?
Kind of.
All right, so we will now go through the finger trick. So first of all, I need to use my fingers here to represent the picture here. Well, let's use the thumbs for the methyl groups. So if I'm going to do the starting materials, should my thumbs be pointing up or down?
Up.
And then my fingers here will represent the hidden hydrogens. So that's this picture here. Okay, and now these are going to rotate. Notice that in this picture, everything's going to be flat, right? In this picture, everything's going to be flat, so I'm going to rotate my hands kind of like this. So the substituents end up flat. Now, should these both be rotating in the same direction or opposite directions? That's right. So let's say I'm going to rotate this one clockwise. If this one goes clockwise, which way should this one go?
Clockwise.
Zzz. So that's it. I rotated them both clockwise. All right, now if you think about it, now we have to use the ideas of inside and outside. Is this thumb pointing inside or outside?
Inside.
And how about this thumb?
Outside.
So that's the answer to the stereochemistry. One of the substituents will end up on the inside, and one will end up on the outside.
So if they both start pointing the same way, one will end up in and one will end up out.
If it's conrotatory.
Yeah.
That's right. So you could draw it like this. If you want to, you can also show the hydrogens, or you can leave those as hidden hydrogens. We didn't even have to show these hydrogens here in the first place if we didn't want to. Those are just the hidden substituents, but if you want to, you can show them. So we can still use the ideas of inside and outside here. In one picture, we'll be talking about up and down, but in the other picture, we'll be talking about inside and outside. All right, well, that's the way to do it. Let's do a few more examples. Let's draw the mechanism in the product here.